continuing on our discussion of methodologies in spectroscopy, mostly talking about Fourier transform spectroscopy in this lecture, as in the previous lecture. So I'm just going to continue on with these week 14 slides. And so now what I probably want to get into are various applications of spectroscopy. And so the first thing that I want to talk about is comparing a single beam spectrum versus an absorption spectrum. So in the previous talk, we talked about absorbance being the negative log of the transmittance. Similarly, we talked about optical depth, right? But for now, if we just focus on absorbance, we note that you really have to have a two-beam technique to pull off an absorption measurement, okay? And so really an absorption spectra is a ratio of single beams. So when I write that the transmittance is the ratio of I over I naught, each of these are single beam spectra that we're ratioing. We commonly call those the background spectra is I naught, and the sample beam spectra is I. And so the way that this works, you know, in a single beam spectra, so it's one single beam of light, right? So you still have an incoming incident light, and you still have an outgoing intensity, right, at smaller intensity. And so we could do a transmittance of just this one single beam. We could do that by taking T of, you know, I over I naught. That wouldn't be very useful though. And the reason for that is, you notice on my picture here, I'm showing you that you can actually get, because this is not atomically smooth, you can get a lot of diffuse reflectance off of this beam. I just had to close the window because I was getting a lot of refraction. How about that? So there's tons of diffused scattering that occurs off of the when the beam hits the glass. Same, you know, as it transmits to the other side, we can also still get lots of diffuse reflectance and even some specular reflectance in case it is a nice smooth situation. Well, this creates a really big problem if you are really interested in what's going on inside the cuvette, okay? So, as is typical in an absorption spectra, you take a single beam of a background. So if you have a sample in a cuvette that's in a solution, you'd have the cuvette and the solvent, but not the solutes. That would be your background single beam, where you record I naught. And then now consider that in your sample single beam, you use the exact same cuvette, but now you fill it up with some molecules. Maybe now you put the actual solution in there. So in this case, I naught here and here will be identical. The intensity of your incident beam on the background or the sample will be identical. Okay? However, the intensity outgoing will be very different for the sample than is for the background. So technically, when you're taking, let's just say transmittance spectra, you're actually taking a ratio of ratios, right? You're doing a ratio of single beams. And so if I call this, let's say this one is the, let's say this is I background and that's I sample, right? Well, because the intensity coming in to the situation, the intensity of light used is identical, those cancel, and so thus your transmittance is the ratio of the intensity of the sample single beam spectra over the background single beam spectra, okay? And then, of course, you take the negative log of this, and that gives you the absorbance. So that's the difference between a single beam spectra and an absorption spectra. Okay. So I'm going to continue along with this in a moment. But for now, let's just talk about garden variety transmission, FTIR. None of you have done this because now we have a much newer spectrometer, but this is what I had to do. I really love this picture right here. I don't know how well you can see it, but here we've got a pile of salt, and this says a lot of pressure and a lot of money, and you can make an optical disc out of that. So, and of course, if we were in the class, I would bring all of my fancy IR optics to show to you, but I don't have access to any of those. But these nice pristine optics that you're seeing, those are salt optics. Those are made typically out of potassium bromide is a little bit better. It's less hygroscopic, so potassium bromide doesn't interact with atmospheric water as much. But what you used to have to do was press these plates, or you might have these things already made for you, these optics. You would drip your sample on them, make a sandwich, and then place that sandwich in a holder, and then the IR beam passes through that thing, okay? And so your background sample, your background single beam, would just be two plates pushed together without a sample. And then your sample single beam would be the sample pushed in there and push them together, okay? And so there's a lot of issues with this. So you can see this is showing you that if you don't have a really nice plate or salt optic made, you know, you can get like all of these effects on the baseline. And now you all know a lot about baselines because you did Spec 1. So you can see this one that's showing you excellent. It's excellent because it has a nice flat baseline. And so that what that really means is the way that you get to that really nice flat baseline is your background single beam has to be identical to your sample single beam, except it contains the sample. And so that means that there's imperfections in your cuvette or in your optic. Then if they're not in the same ratio, right, based on this picture here, if those optics are not in the same orientation that they were from background to sample, then you're going to get baseline effects. And those baseline effects can really make a difference in seeing certain features. I mean, like if we look at this pitted plate spectra, it almost looks like some of these are actual peaks, like they're actual features, but they're not, okay? So that's why this technique, there's a newer techniques that's used now, which is what you all did, and I'll describe that here next. And so that's called ATR FTIR, so attenuated total reflectance. So this is the exact type of sample accessory you used. So all FTIR spectrometers are virtually identical. They all contain a Michelson interferometer. They all contain a helium neon laser that sets the sampling interval and gives you the resolution. They all contain a detector. They all contain a hot metal disc that makes the IR radiation. The only difference between various FTIRs are the sample holders, okay? So in this transmission FTIR, it's hard to see it, but that's the sample holder. It's just a little thing that goes right in the path of the beam that holds the optics in place. So the beam just passes straight through. I think I can draw that better right here. So here's like a little holder. That optic sandwich is like, you know, fit in the middle right there. And then the IR beam just literally transmits right through to the detector, okay? So we'll say this is TFTIR. Transmission Fourier transform infrared spectroscopy. So now ATR FTIR, you put one of these little accessories in the path of the beam. And there's some complicated optics in these things. So what you all used, what we have in the 5th floor of Science A is a single bounce ATR. And the way that single bounce works, as you can see from the picture, let's zoom in on that. So you have some type of crystal. The one that you guys use upstairs is actually a diamond crystal. It's pretty cool. It's very expensive, crazy expensive, but it's not going to get damaged. It's IR transparent. It can't be, there's not a single solvent that's going to dissolve that diamond crystal. So that's pretty typical. Other ATR crystals that are common are zinc selenide. That's actually my favorite. Zinc selenide is not as strong as diamond, but it's chemically inert, which makes it really useful, and I'll tell you why in a moment. So in an ATR sample accessory, your sample goes on top, and if you remember in OChem lab, right, you just pipetted a little liquid drop in that holder. So the IR beam is coming right off of the Michelson interferometer, right? All wavelengths simultaneously. It goes through this ATR crystal and actually creates an evanescent wave in the sample. And so you might be saying, what is an evanescent wave? Well, we've actually already talked about evanescent waves in tunneling, okay? So the evanescent wave, let me draw this bigger. So now imagine that I have some barrier with potential energy V, and I have an incident beam coming in on this side, okay? I will get an evanescent decaying wave inside the sample, and on the other side, we know it will transmit at lower intensity, okay? So when we put this into this ATR, right, our evanescent wave, so suppose this is our little like liquid droplet, right? So our sample's coming in, okay, we're going to get this decaying evanescent wave that will actually be absorbed by the sample, and then on the crystal, you'll get a total internal reflection off of that boundary. So we talked about that. Let me just scroll up to that really quick. Yes. So you're getting a total internal reflection as pictured right here. But right here, where you have that reflection, you get a little bit of tunneling into the sample. And so that's what we call the evanescent wave. And so that means that the reflected beam that's coming off, the specularly reflected beam, will be at reduced intensity. So this will be I0 and this will be I. Okay? So that's called a single bounce ATR crystal, where only literally one bounce happens. The really sensitive ones are called multi-bounce, and this actually allows you to do quantitative IR at very, very low concentration. So this is only showing you 1, 2, 3 bounces, but a typical multi-bounce IR ATR accessory might have as much as 20 or even 100 bounces. And so the effect of that is it makes a longer path length. So remember Beer's law, A equals, let's see, epsilon times concentration times path length. So for the same concentration and same molar absorptivity, if you have a longer path length, you can get more absorbance. So this is how you can do very low concentrations, is by having a multi-bounce ATR accessory. I have a really cool germanium ATR accessory, and I didn't bring it home. I wish I would have. You've probably never seen germanium before. It actually looks a lot like graphite. It just looks like this kind of silvery hunk of graphite, which is pretty cool. And it's a solid piece, so it doesn't look like it's an optic, but it's an IR optic, right? It doesn't have to be transparent to the visible, okay? So, and again, zinc selenide is also another common ATR optic because of its IR transparency. And zinc selenide is a really pretty yellow color. I think I have a picture of one coming up. Okay, so now I think I have a picture of one. Oh, maybe I don't. I'll have to dig one up. So, so this is the ATR accessory. There's one more famous type of ATR, or excuse me, FTIR accessory that I'm going to talk about, and that's called a drifts accessory. And drift stands for diffuse, reflectance, infrared, Fourier transform, spectroscopy. So recall, diffuse reflectance is this, right? It's where you have a roughed surface and the light scatters in all kinds of different directions, okay? So in a drifts accessory, oops, let me find it. Here we go. Okay, so you have a sample holder, okay? And you have a series of convoluted mirrors. So not all drifts accessories are the same. except for the fact that they all contain an elliptical mirror. So some of them are called the praying mantis because the accessory actually looks like a weird little praying mantis. The optics, I'll try to dig up a picture or Google praying mantis drifts. You'll see it. They look like a praying mantis. It's really cool. This is the drifts accessory that I have. And so there's an elliptical mirror over the sample surface. And as you can see from that zoom in, what happens is light from the Michelson interferometer, so this is still just a regular old FTIR, you just place this whole accessory down inside the sample compartment. So light from the Michelson interferometer bounces off these mirrors, bounces off the elliptical mirror, and then scatters diffusely off the surface of the sample. This is why you have an elliptical mirror, so it can catch all of these different angles and then sends them back and on to the detector. Okay? So the advantage of drifts is there's no sample prep. That's what all the textbooks say. I say they're big fat liars. We have to do tons of sample prep. But the real magic behind drifts is that you're doing a powder solid and you're only analyzing the surface of the powder solid. So in that ATR, as you all know from experience, you can still do a powder solid, right? You loaded solids into that little ATR crystal, but you're getting the bottom of the sample, right? In drifts, you're specifically sampling the surface of the sample, which means you can do really cool heterogeneous surface chemistry while taking an IR spectrum at the same time. So this is what we call difference spectroscopy, or sometimes action spectroscopy. And the idea behind this, so remember we talked about single beam spectra and absorbance spectra. So imagine that you have two different conditions, condition 1 and condition 2. And in condition 1, you still have your sample. This is not a background. This is the sample that you want to investigate. You take a single beam spectra, okay? So now, suppose something happens between condition 1 and condition 2, like time, or, well, obviously time is going to happen, but what's going to happen in that time? Maybe chemistry, maybe a physical transformation, a phase transition. So whatever happens between that time, right, something happens, record another single beam spectra. So now you take the absorbance, or transmittance if you like, ratio between condition 2 and condition 1, and the spectra will only reflect the change that happened. So for example, if nothing happens between condition 1 and condition 2, you're just going to get a flat line, right? Like some noise. So that little wiggle corresponds to the shot noise of the detector. But if, let's say, a new functional group grows in between condition 1 and condition 2, so you're doing some type of chemical reaction, and this doesn't just have to be drifts. You could do this via the ATR. What's really special about drifts is you could do a chemical reaction on the surface of that sample, and then the drift spectra will see it. Okay, so if a new functional group grows in, you'll see a positive peak like this, okay, which is pretty cool. But if a functional group disappears, so I should say that this is absorbance, and this would be 0, right? And these would be positive values, and these would be negative values. But if a functional group disappears, then you might see a spectrum that looks like this. You'd get a negative peak, okay? And so you'd have to, of course, take a what I will call a survey spectra to see what's there first. And a survey spectra would just be your normal garden variety ratio sample to background. Okay? So that tells you where the peaks are. But now, if you've still got your sample parked in there and you do some chemistry on it, you won't actually see a survey spectra. You'll see a difference or action spectra. And so I've got a couple examples here on the slide, and then I'm going to show off some stuff that PChem did last year, as well as give you a very short, like 3-minute spiel on my own research where I use different spectroscopy to elucidate chemical mechanisms. Okay, so here's a really famous result that actually came out of the group that I worked in grad school, 2007 at UC Irvine. So this is really cool. So this reaction, let me write the reaction down. This is the oxidation of sulfite with ozone to make sulfate. Okay, so ozone is a powerful oxidizing agent, and it will oxidize sulfite to sulfate. So if you look at the spectra, here's the dark looking spectra, Spectra A, which is just sodium sulfite, pure sodium sulfite. So you can see there's no stretching associated with sulfate. So sulfate shows up at 1100 wave number, the oxygen sulfur stretch, and sulfite shows up around 950 or so. Okay, so with just pure sodium sulfite, there's nothing there. Okay, and so this sodium sulfite spectra, that would be your survey spectra. Okay, so then now what happens is you start pumping in ozone over the surface. Okay, and as you start doing that, after 5 minutes, some of that sulfite has reacted, so the peak has gone down. And correspondingly, if you look at this, here's the gray one in the middle, some sodium sulfate, some sulfate has showed up. So at this 5-minute interval, you've still got some sulfite and some sulfate present. And then now after 15 minutes, all of the sulfite has been converted over to sulfate. And so this is really cool. So you can now do kinetics on reactant decay and product evolution at the same time, which is really, really cool. So I'm going to show off an experiment that we typically do in PChem lab. I'm going to go over to this presentation here. So those of you in PChem lab, I'm awful sorry that you guys don't get to finish off your projects. This was a project that a student last year, Amelia MacArthur, did. So what she and her lab mates did was they synthesized the compound nitritopentamine cobalt 3. So if it's been a while since you've done nomenclature of complex ions, so here's the cobalt 3, and it's pentaamine, so 5 amines, 1, 2, 3, 4, 5, and then nitrito is if the ligand is attached via the oxygen, so ONO cobalt. Okay, so it's a really unstable bond, and actually this molecule has to be synthesized. It's not commercially available, and it has to be synthesized in the dark and as cold as possible. So I make P-chemists do synthesis, and of course they'd have to do the most insane, crazy hard synthesis. So it's pretty fun watching students like work in a dark hood. I don't turn all the lights off in the lab, but they basically put like a cardboard sash over the hood, and you're working in there in the hood full dark. So it's really hard. So this compound, when exposed to light or heat, will spontaneously isomerize into nitropentamine cobalt 3 chloride. So in other words, the bond goes to the more stable oxygen cobalt bond. That's the more stable configuration. So it's a spontaneous isomerization, which means it's a first order reaction. The reaction can go in the solution phase or the solid phase. And we've been doing this experiment for several years, and most students have chose to do it in the solution phase, which means they characterize it via UV vis. These are colorful molecules. But Amelia and her lab mates last year, for the first time in PChem in 363, did this in the solid phase, which is really, really cool. It's very difficult to actually study an isomerization reaction in the solid phase. And so, of course, they use drifts. So I'm going to skip through a couple things here. So this was like her presentation. So this is kind of background, like how the drifts work. So here's like a slightly better cartoon. The IR beam comes in, hits elliptical mirrors, scatters in all different directions, and these elliptical mirrors allow the light to come back. So I'm only showing you like the specularly reflected beam, but consider all of these diffusely reflected beams will still be collected and onto the detector. Okay. Oh, here's my zinc selenide optic. So you can see how that's yellow. So that's not a yellow sample. That's actually a yellow optic, a yellow zinc selenide optic. Okay, so here's another picture. Okay, so the so here's differences between the nitrito and the nitro. The nitrito has various stretches at 1687. The nitro has 1528. So there's differences between the nitrito and the nitro compound. Here's what it actually looks like in the drift cell. So let me just back up for a second. So this picture, there was a white powder solid. It was not the same experiment. I just let Amelia use this picture for her talk. So there's a white powder solid, but it's a yellow zinc selenide optic. So now this is a picture of their sample, and this was that nitritopentamine cobalt compound right before they started doing the experiment here. And of course, it's being exposed to light. So right after this picture was taken, they got the experiment going through the kinetics. But you can see it's a powder solid. It's loaded right in there. And the way these elliptical mirrors work, so you can see there's a groove right there. Those elliptical mirrors are going to close over the sample to complete the optical pathway. So here are survey spectra of the nitrito isomer and the nitro isomer that was done via ATR. Okay, and so they look very similar. So you can see they're these are corresponds to the amines. So the amine stretching region looks very similar. The amine bending region looks very similar, but there are some very subtle differences in the fingerprint for the O-N-O cobalt bond versus the N-O cobalt bond. So I won't go too much into detail the subtle differences, but there are some just very slight differences on these survey spectra. Okay, so now this is a look at the drifts spectra, and this is so cool. I was so stoked when Amelia and her lab partners got this data. As noted by the legend, it actually took them several days, so it's a very slow reaction. So you can see at 120 minutes, that's the red spectra, nothing has changed, right? You can see that after 120 minutes, there just hasn't been a lot of change. So the ratio of these two, so the original background single beam was just of the nitrito, right? And all they did to record these drift spectra was just after 120 minutes, record another spectra and ratio it to the spectra from 120 minutes prior. This 388-minute spectra was they recorded a spectra and ratioed it to the spectra from 388 minutes prior, and so on. And so they did this for several days. I was really impressed. I think one of Amelia's lab partners stayed up all night just recording spectra after spectra after spectra. And what's so cool is, so you can see here, again, the red line means nothing's happened, but now you can see over time, this peak is growing in, and this peak here at about 1080, that peak is unique to the nitro isomer. Or excuse me, that peak is unique to the nitrito isomer. So what's happening here, this is actually that that in cobalt stretch where the nitrogen is bonded to the cobalt. And so that peak is disappearing. So you can see negative values, right? So that tells us that the peak is going away. You can also see there's another competing peak on there, which is why doing that data convolution you did in Spec 2 is really important, right? There's competing peaks in the same region. But then now this peak here and here and here, so these are all differing peaks. And you can even see that there's some really interesting stuff going on in the ammonia region. And so we could elucidate stuff about the mechanism, but we didn't for this experiment. But this peak, Amelia chose to use as the product evolution peak, and you can see it's growing in. And so now, and again, this would require some data deconvolution if we wanted to get the area, because you can see there's probably two peaks under there. But they just looked at the peak absorbance. So this is taking the peak absorbance at that 1080 wave number peak, and this is the peak absorbance at that 1282. And this is so cool. This was I was jumping up and down in the lab when they got these results, because it was the first time we did this experiment, and it worked beautifully. You can see wonderful first order decay. Isomerization is a first order process. Rate constant was 7 times 10 minus 6, basically plus or minus 1. And then here was the product evolution. and then they got the rate constant to be 6 times 10 to the minus 6, plus or minus basically 1. So that tells us we're looking at the right peaks. You know, the fact that the rate constant is the same, but you know, one is showing a decay and one is showing an evolution. So super, super cool application of spectroscopy to do kinetics. And they tried on a couple other peaks, but as you can see, this, or a couple different temperatures rather, this was 55 degrees, and that worked really well at 55 degrees. It got bigger. This got a little chaotic. At 72 degrees, it was even more chaotic. So they got 4 different temperatures, which allowed them to get an activation energy, natural log of K versus 1 over T. I was going to challenge PChem this year to redo this experiment at different temperatures and try to get a better activation energy and work out some of the mechanism details. But, you know, we're all here at our houses, so we can't really do that. So I want to show just one more thing you can do with drifts. This is what I do in my research. So shameless plug on my own research. So what I'm interested in is heterogeneous atmospheric chemistry. I'm interested in how small gas phase molecules, volatile organic compounds, such as something like acetone, could get picked up by an aerosol, in this case mineral dust, and then you know, physically stick to that particle and then get transported long distances. So, you know, I hypothesized that would create like this organic layer. That organic layer could react with, you know, ozone, relative humidity, light, etc. So what's the chemical composition of this layer? Can it pick up other organics, etc.? So let's see. So this is how I've got the drift cell set up for my own experiment. So here's that picture. Once again, that's where it came from. And then now the way that I'm using the drift cell here in this research is I've got this complicated manifold that creates a synthetic mixture of gases. So I basically make my own atmosphere. And those gases come through this tube and they flow over the surface of the sample and then get pumped out. And so the idea now is, and so here's my beautiful yellow zinc selenide optics. The idea here is we're recording spectra in time as those gases are being passed over a surface. And there are certain things that will allow us to see if the gas actually absorbs and sticks. And that's mostly related to the fact that cross sections in IR are very small and it's very difficult to see gas phase organics unless you have a very long path length. But also if some chemistry happens, we're going to see an evolving spectra. And down here are like some examples, you know, positive peaks showing functional groups being created, negative peaks showing functional groups being destroyed. And so this was kind of what we hypothesized the reaction should be. We hypothesized 2 acetones should be catalyzed by our surface. EMO stands for environmental metal oxide. And they should undergo an aldol condensation to make acetyl oxide. And if they keep reacting, it'll undergo another aldol condensation to make isoferrone. So here's some of the data. So there's a lot going on. I just kind of threw this together as like a really quick and dirty research talk to highlight what you can do with drifts specifically. So over here on the left, all of these spectra in black, these are the survey spectra. So these just show that, so what we did was flowed gas phase acetone over the surface of our metal oxide, and these spectra show that it actually stuck. So we have simultaneously a negative peak and a positive peak. That negative peak right here, 3670, that corresponds to a hydroxide stretch. This peak right here at 1703, that corresponds to a carbonyl stretch. And so basically as our gas flowed over the surface, it displaced some adsorbed atmospheric water, right? The hydroxide stretch was displaced, and what resulted was a carbonyl stretch. And the reason why this is a very sharp single hydroxide instead of the broad, like symmetric, asymmetric, like we talked about, is because these are bound hydroxides. These are not like liquid water where there's a symmetric, asymmetric stretch. So it's just a single bound hydroxide stretch. So then what we're able to do is either, we could do this in time. Let me back up or go forward. Oh, here we go. So on the absorption studies, what we're able to do, you notice here the 0 minute, that would be like ratioing identical single beams to each other. So it doesn't show anything. It's a flat line. But then we turn the acetone flow on and start recording spectra in time, and we can actually see it. I got excited and pushed the button again. We can actually see it absorb, right? You can see the carbonyl peak grows in with time. And then similarly, we can turn the acetone off and watch it desorb. We can watch it evaporate. And so you can see that as well, that the carbonyl starts decaying. And we do this, so this is just keeping track of the peak absorbances. So here's peak absorbance versus time. And here's an absorption spectra, so we're putting acetone on the surface. And then this line indicates the point in time where I turned acetone off, but we just kept recording spectra, and then you can see it decays. So now what I did over here, so these are like different samples. We made 5 different samples, sample 1, 2, 3, 4, and 5. Sample 2, as it turned out, nothing happened, and we're still trying to figure out why. But if you notice this, right, the absorption profile, it takes on a first order Langmuir adsorption equilibrium profile. So that means it's going to be a first order evolution, and then it's going to hit equilibrium and then stop, right? And that's great that we proved. So you can see we proved that it hits equilibrium, which is really cool. But you can see different samples had different peak absorbances. So what I did instead was normalized all the signal. And when we normalize all of those signals, they all look identical. So they're all normalizing, they're all going up at the same rate. And then also we can look at the normalized desorption, and you can see it decays. And what we proved with this, what's really cool, you can see because it doesn't desorb all the way down to 0, like this 0.7 means there's 70% of it remaining. That proves that the acetone is stuck to the surface. So that was a really cool thing we did. And then the last thing we did, we actually see evidence here of a chemical reaction. So on some experiments, when we really cranked up the acetone concentration, we're going to have lots of acetones in proximity with each other. So that's where this aldol condensation comes in, when those two molecules are in close proximity. And so then as we started recording spectra in time, you can see we had a really dynamic looking set of drifts spectra. So you can see these hydroxide peaks grow in more negative. So I'm not going to summarize this mechanism. I did this in a previous talk. But basically, if we look through the spectra in time, it more or less confirms this mechanism. So just as one example, right, in the first step, you get acid catalyzed enolization. So that creates a new hydroxide stretch, which is what we see right here. So here we're seeing this new hydroxide stretch, or excuse me, not this new hydroxide stretch, rather, with this acid catalyzed enolization, it has water, right? This is an aldol condensation, so water is created. So here, this red, that's the water spectrum, right? That has the asymmetric, symmetric stretching. And so it happens early on. I guess I am going through this mechanism after all. So it happens early on in the mechanism, right? Where you make water, and we see that early on in our time. Another step that we thought was really cool was the creation of carbon-carbon double bonds, which is what's going on with this 16O2 right here. So you can see later on in the mechanism, there's actually the double bond gets created, and we can see that double bond growing in. And it's fairly consistent with literature spectra. So again, you can do some really, really cool stuff with this drifts. So just trying to give you a highlight of what chemists like myself use spectroscopy for. Okay, folks, so that'll be the last lecture for this week. So your quiz mostly just going to be asking you conceptual information, highlighting the differences between the techniques I've talked about. So the main techniques I've compared are dispersion spectroscopy and Fourier transform spectroscopy, as well as some of these different accessories. You should know the difference between a single beam spectrum and an absorbance spectrum. You should know the difference between a survey spectrum and an action spectrum. So a survey spectrum is just your traditional sample background, okay? An action spectrum is when you have no background. Your sample is your background, and you're doing something and recording spectra over time. All right, folks, so there's just going to be one more set of lectures that I record next week, and that'll be it. See you later.